Hello everyone, welcome to ChemBrain YouTube channel, your only ultimate destination for learning chemical engineering and chemistry courses. I am your host and your tutor, Andy Agro, and I'm happy to see you here once again. And today we'll be learning about chemical kinetics. Okay, so let's take, for instance, we are burning a candle. So if we are burning a candle, what do we observe? We observe that the candle flame produces heat and also produces what? Light. However, with time, we also observe that the wax begins to what? To diminish. Based on this illustration, if we are asked to identify what are our reactants, then we could clearly say that our reactant is the wax and also the oxygen we derive from the air to support the burning. And our product will be the carbon dioxide we are releasing into the environment, the water vapor, and also heat, okay? Now, let us also consider some of these factors that aid or that support the burning process. We can think of temperature, okay? So looking at temperature in this equation, we are saying that if we have two candles and we increase the temperature of the other candle higher than the other, then we automatically expect that the candle with higher temperature is going to burn at a faster rate compared to the other, which means that temperature is a key factor in chemical kinetics, okay? Now, let us also consider this example. If we have broken pieces of this candle flame and we have a bigger candle flame, which of these two is going to burn or is going to finish burning earlier? We are expecting that the smaller pieces of this candle is going to burn at a faster rate. Why? Because breaking them into pieces means we have increased the surface area, and therefore a surface area is a key factor that also influence the kinetics of a reaction. Now, let us also consider the elements which are present in the wax, okay? So let's consider this element to be a catalyst, which means that catalyst or the type of catalyst is also an important parameter or factor that also influence the chemical kinetics. Based on that, we can put the representation of candle in this equation form, okay? So let's put chemical equation of a candle in this form. So we have our was in this form, which is the was, okay? We have the oxygen we are deriving from the air, the CO2, the water vapor, and heat. Based on this chemical representation, we can clearly say the was is going to be our limiting reactant, and the oxygen, of course, going to be an excess reactant, because we are going to still have more oxygen in the environment to support burning of the wax, okay? So what is limiting reactant? If we say limiting reactant, we basically means that any compound that finishes in the course of chemical reaction. And what do we mean by excess reactant, which will automatically be an opposite for limiting reactant? So an excess reactant is any reactant that do not finish in the course of chemical reaction, okay? Now, let us also think about rate law. Now, to say rate law are just an empirical, this is rate law, and rate law is just an empirical equation. And this empirical equation provides more information about the rate of the reaction and also the concentration of the reactant, okay? Now, let us see, as chemical engineers, if we want to develop some chemical empirical equations or models, okay, to study the mechanism of a reaction, okay, we may not have a clear idea or a precise idea about the formation, okay, but we may have an idea about our starting materials. Therefore, we start from the known to solve the unknown. So the same applies to rate law. If we want to develop rate law, it's just empirical equation. So if we want to come out with an empirical equation to study the mechanism of a reaction, then our focus will be on the reactant and not the product. Our focus should be on the reactant and not the product. So in rate law, we write rate law for reactant, okay, and not product, okay? So now we have K, which is the rate constant, times the concentration of the Was and also the concentration of the oxygen, all raised to their order, okay? This is the order of reaction. This is the order of reaction, okay? The same applies to this one, okay? Now, let's assume that in this chemical equation of burning a candle, the stoichiometric coefficient of each of the compound is 1, okay? Let's assume that we have coefficient of 1, we have coefficient of 1, this, the same, that, and that. So in this case, what we mean is M is not equal to 1 and N is not equal to 1, which means that the order of reaction is not the same as the stoichiometric coefficient. The order of reaction is determined experimentally. It's only determined experimentally, okay? Now, let us also consider what is rate of reaction. To say rate of reaction is just simply something that happens within a unit time. So now engineers try to study how fast a reaction is disappearing or consuming and how fast the product is also forming, okay? So now with rate of reaction, we concentrate on reactant and also on product. So we can write rate of reaction for reactant, okay? Then we can write rate of reaction for product. So now in writing the rate of reaction for reactant, we bring our negative sign, which indicates disappearance, okay? So in chemistry or chemical engineering, the negative sign means it is consuming or it will finish with time, okay? Now the delta here, this delta here in chemistry means change. Now, if we have this bracket sign, also means concentration. So what is changing? The Was is changing with what? With time, okay? Now, if we want to write for oxygen, then oxygen will also be negative because it's a reactant and it will disappear. Then the delta means change. What is changing? Concentration of oxygen with also with time, okay? Now, what we need to do is we need to divide each equation by their stoichiometric coefficient. So the stoichiometric coefficient of Was is 1, so we divide by 1. That of oxygen is 1, so we divide by 1. And any number by 1 is the number itself, okay? Good. Now, let us also write the rate of reaction for the product. To write the rate of reaction for the product is about formation. Okay, so now if something is forming, then it's like accumulation. We are getting more. So in chemical engineering or chemistry mindset, what we do is we represent it with a positive sign or a plus sign, which indicates that formation. So the plus sign means that there is formation. Okay, so now delta means change. The oxygen level, the CO2 level will be increasing. So we have change in the concentration with time. We have change in concentration of water vapor with time, okay? Then we have change in concentration of heat also with time, okay? Great. Now what we need to do is we need to divide each of these equations by their stoichiometric coefficient. So we have 1, we have 1, and we have 1. Very good. Now that we have gotten the gist of rate law and the rate of reaction, let us also look at how we can derive some integrated laws. Okay, now let's consider the zero order reaction. So now to derive the zero order reaction, we will first consider a hypothetical equation. So let's say A, which is a hypothetical equation, okay? It's giving us a product. Now, what we need to do is we need to write the rate law for A and also the rate of reaction for A. So to write the rate law, okay? So to write the rate law for A, then what are we going to get? We are going to get the rate constant K and also the concentration of what? Of A. Okay? Now, what is the order of reaction? In this case, since we are assuming that the order of reaction is 1, is 0, then we can put the 0. If not, then it means the order of reaction is determined only experimentally. So we will put there with any variable, okay? So we could say that maybe the order of reaction is M, is X, is Y. But now we assume that the order of reaction is what? Is 0. So we can put the 0. So which means that any number raised to the power 0 will give you 1. So it means the rate law is K. Okay, so this becomes our equation 1. Now let us also write the rate of reaction for A. Now the rate of reaction of A is about the disappearance, okay? So if A is disappearing, then we bring our negative sign, then we'll bring change. With time, it will be changing. We'll bring our concentration. What is changing? Concentration of A with time, okay? Now, we can also represent this change with a differential form, which we can say the D, which means we want to study the instantaneous change, okay? Not the average change. We want to study the instantaneous change with time. So we can also represent it by dt. That is the differential form, dt. So we have equation 2. So now, if we are assuming that the rate law and the rate of reaction is the same, okay, then we can equate equation 1 to equation 2. So we can equate, what we do is we have to equate 1 and 2, okay? We need to equate 1 and 2. So if we do that, then we have K is giving us negative D of the concentration of A with respect to the differential of dt. Now, what we need to do is we need to group like terms, okay? So we take dt to the other side and the concentration to the other side. So we have K dt. We bring the negative sign here. We have that of the differential of the concentration of what? Of A, okay? Now, what we need to do is we want to study the change of concentration with respect to time. So we have to integrate both sides. So integrate. Okay. Now we need to integrate. So let's integrate. This is Jean. Okay. So now if we integrate, we have this. We are integrating from 0 to certain time of dt. Okay. Then we also integrate from the change in A naught, from that is the initial concentration, to a certain concentration of 80 of dA. Okay, great. Good. So now what we do is if you have an integration of a differential sign, then we get the variable itself. So we have T is equal to the same as the concentration of A. If we integrate a differential variable, we get the variable itself. So we have still concentration of A. But the concentration of A is changing from A naught, integral A naught, to a certain time of A, okay? Now what we need to do is we need to substitute these integrals into this concentration of A. However, we need to subtract initial integral from the final integral. So we have negative KT is giving us the change in AT, okay, minus change in A naught. Okay, now what we need to do is we need to make the change in T the subject. So we have change in AT is giving us negative KT plus that of A. Okay, now what we need to do also is to compare this equation to equation of a line, which is MS plus C. So if we compare to the equation of a line by plotting y against x, then our slope is m and intercept c. So if we plot a graph of change in t with time, our slope is k, which is a negative slope, and our intercept is the initial concentration. Okay, so now let's plot a graph of change in concentration at a certain time, t with time. So if we have negative slope, then it goes like this. Okay, so this is our slope. Then this becomes our intercept, which is change in A naught. Okay, our negative slope. Okay, this becomes our slope. Okay, great, great. So now let's try also to do for first order. Okay, now to also prove for first order, we also have to still consider a hypothetical equation. So let's assume that this hypothetical equation A is giving us a product. Good. Then now what we need to do is we need to write a rate law and a rate of reaction for A. So let's see rate law. So to write rate law for A, we have the rate constant K and the concentration of what? Of A. Now, since we are assuming first order, then our order of reaction is what? 1. Okay, so now we have K, which is the rate constant, then the concentration of what? Of A. Okay, so we have equation what? 1. Now let's write the rate of reaction for A, which is the rate of disappearance because it is a reactant. So the rate of reaction, let's consider the rate of reaction of A. Now we have negative, we bring our delta, which is change. Then we bring our sign, which is concentration. What is changing? A is changing, and it is changing with what? It's changing with time. Now we can also express the delta in differential form, which means we want to study the instantaneous change, okay? So we just represent the delta with D, which is the differential form. So we can also represent it in this form. So we have equation 2. So now if we assume that the rate law and the rate of reaction is the same, we will get the same value. Then we can equate equation 1 to equation 2. So equate 1 to 2. So if we equate 1 to 2, we have the rate constant and the concentration of A is equal to negative D of A with time. Okay, now what we need to do is we need to group like terms. We take dt to the other side and concentration to the other side. So we have negative K dt is giving us negative D of concentration of A, okay, of concentration of A. So what we did is we divided this side by concentration of A, then we also multiply through by dt, okay? So we have this equation, we have this form. Now what we need to do is we can also rewrite this in another form as negative K dt is also equal to, we have 1 over, let me clean the negative sign because I brought my negative sign here. Great. Good. So we can also write it as concentration of A. Then we can write D of concentration of A. Okay. So now what we need to do is we need to integrate the change in concentration with respect to what? Time. So we have this and we have that. And once we integrate a differential, we get the variable. So we get T. Okay. We are integrating from not from the initial to certain time. Great. And we are integrating from 0 to also certain time t. So we have this. And anytime you integrate an inverse variable, then we get a ln of that variable. So we have this. Okay, then we bring our integral. Our integral is changing from a naught to certain time at t. So now we substitute into the equation, but we need to subtract the initial integral from the final integral. So we have negative change in at minus ln of change in a naught. Okay, good. Now what we want to do is we want to make this the subject. Okay, so let's make that the subject in the equation. So we have ln change in at will give us what? Will give us negative kt plus ln of change in a naught. Okay, now what we need to do is we need to compare to equation of a line. We have y is equal to ms plus c. So if we plot a graph of lane change in at with time, then we are going to get a negative slope. Great. Okay, get a negative slope. Then our intercept will be lane of a naught. Always understand that anytime we have a logarithm number or anytime lane is attached to a number, it becomes dimensionless. So this is dimensionless and this is also dimensionless, which means that the units of the rate constant k in first order will be what? Per seconds. Okay, great. I hope you really enjoyed today's lesson. You can do same for second order, third order, and so on. Please like and subscribe for more videos. Thank you for watching.